There's a moment in almost every Belgian Malinois wall climb video, usually around frame 47 if you slow it down, where the physics stops making sense. The dog hits a vertical surface, full weight, full gravity, and instead of sliding back down like every other material object subject to Newton's laws, it goes up. So I want to walk through exactly what's happening in that moment, because the engineering is stranger and more specific than most people realize. And it tells you something about why the Malinois dominates military and search and rescue units globally, when a dozen other breeds don't even come close. The instant a 27-kilogram Malinois makes contact with a vertical surface, two forces are in direct competition. Gravity pulls straight down at 265 newtons. To counter that, to not slide, the dog's paws must generate a frictional force equal to or greater than that same 265 newtons. Friction, in this context, is the product of two things: the normal force pressing the paw into the wall, and the friction coefficient of the paw pad material against the surface. On dry, untreated plywood, the standard training wall material in most Schutzhund facilities, that friction coefficient sits around 0.7, which means to generate 265 newtons of upward friction, the dog needs to press laterally into the wall with at least 378 newtons. That's roughly 85 pounds of lateral force. From a 60-pound animal. Let that sit for a second. That lateral force doesn't come from nowhere. It's not muscular strength alone. It comes from momentum and the specific geometry of how the Malinois redirects it. The approach is where most of the physics budget gets spent. A trained Malinois reaches sprint velocity between 6 and 7 meters per second in the approach run. Call it 6.5 meters per second for a mid-range estimate. Plug that into the kinetic energy equation, 1/2 times mass times velocity squared. You get roughly 570 joules of stored kinetic energy at the moment of contact. Now, if the dog did nothing after hitting the wall, if it were just a projectile converting horizontal momentum to vertical, that 570 joules of energy would theoretically lift a 27-kilogram object 2.15 meters off the ground. Pure inertia. No muscle involvement beyond the initial sprint, but documented Malinois wall climbs reach 3 to 3.6 meters, sometimes more. The difference between 2.15 meters and 3.5 meters isn't aerodynamics. It's the active climb phase, the period where the hindquarters are still in contact with the wall and generating propulsive torque. That's where things get genuinely complicated, and where I think most people analyzing this breed get it wrong. When the hind paws engage the wall surface during the climb, the hip extensors, primarily the biceps femoris and semitendinosus, contract to produce a torque about the hip joint. The moment arm here is the horizontal distance from the hip joint to the paw contact point on the wall surface. In a dog driving vertically upward, that moment arm is relatively short, but the angular velocity is high. Power output, in rotational mechanics, is torque multiplied by angular velocity. The Malinois hindquarters aren't generating enormous torque by dog standards. A Rottweiler generates more raw force. What they're generating is fast torque, applied in rapid, repeated bursts during the brief window of wall contact. Each stride cycle during the climb lasts somewhere between 80 and 120 milliseconds. The dog's nervous system is firing hind limb extension commands at a rate that most breeds physically cannot match. It's closer in principle to the fast twitch fiber recruitment you see in sprint athletes than to any kind of strength-based movement. I spent a while trying to find precise electromyographic data on Malinois hind limb activation during vertical locomotion. Couldn't find it. The research doesn't exist in any published form I could locate. A biomechanics graduate student named Tomás Vázquez at UC Davis was apparently building a study on it in 2021, but whether that got published, I genuinely don't know. That gap in the literature is more interesting to me than the gap itself suggests. It tells you how little formal attention has been paid to what is, structurally, one of the more unusual locomotion patterns in domestic canids. Now here's the thing people miss when they compare the Malinois to the German Shepherd. The standard argument is that the GSD is heavier and less agile. Both true. But the weight difference alone doesn't explain the vertical performance gap. A well-conditioned GSD can generate similar approach velocities. Similar friction coefficients, similar hip extension power, pound for pound. What it cannot replicate is the spinal geometry. The Belgian Malinois has a nearly level top line. The line running from the withers to the base of the tail is close to horizontal. The German Shepherd, by contrast, has been selectively bred for a dramatically sloped rear top line. That rear angulation changes the angle at which the lumbar spine transmits force from the hindquarters to the rest of the body during the climb. On a vertical surface, the Malinois spine functions approximately like a rigid column in compression. Forces transmit efficiently along its long axis. The sloped GSD rear creates a bending moment in the lumbar region during vertical loading. The dog is essentially fighting its own skeletal geometry to transfer power upward. The structural analogy would be comparing a vertical load-bearing column to one that's pre-angled. Identical material, different force paths, very different efficiency. This is why Schutzhund trainers have known for decades that the GSD's wall performance plateaus earlier than the Malinois. It's not a conditioning problem, it's a lever problem. The Malinois spine-to-hip geometry gives it a mechanical advantage in vertical loading that you can't train into another breed. You'd have to breed it in over generations, which is, accidentally, exactly what happened, though nobody was designing for wall climbing. They were selecting for patrol work, for herding, for drive. The wall climbing is a byproduct of the same structural traits. There's something genuinely unsettling to me about watching a Malinois decelerate at the top of a wall. I've slowed down footage from Belgian ring trials, where the dog crests a 3.5-meter obstacle and lands with what looks like deliberate control on the other side. I still don't fully understand the neural mechanics of how it dissipates that much momentum without apparent injury. The deceleration phase is its own physics problem, and one I'd put in a separate video. What I do know is that the climb itself, from approach to crest, is one of the more precise pieces of biological engineering in the working dog world. Not because it looks dramatic, because the tolerances are tight. The friction margin, the torque window, the timing of hindpaw release. Any one of those off by a measurable fraction, and the dog drops. The breed gets it right, consistently, at heights that would end careers for most of its competitors. There's a breed most people don't think of when they discuss vertical locomotion. Something smaller, closer to the terrier side of the working registry. The structural constraints are completely different. If you want to analyze the wall geometry for that one, put the breed in the comments and I'll run the numbers.